Hi, good afternoon to Dr. Fairuz. We are from Group 18 and we're going to present about KIL 3012 Process Equipment Design Case Study. So before I begin the entire presentation, I'd like to talk about the introduction to distillation column. Distillation is the process of separating components in a liquid mixture by boiling and condensation based on the different volatility. There are many types of distillation such as simple distillation, fractional distillation, which is used in the oil and gas industry, steam distillation, and vacuum distillation. Now, there are few components found in the distillation column which are essential for the distillation column to work. The first one is the vertical shell, in which is where the separation process takes place. Secondly, the column internals such as trays or plate packings, reboilers, condensers, and reflux drums. Finally, I'll talk about the applications of distillation column. Is majorly used in the oil and gas industry to separate crude oil to produce different kind of oils for our daily use. Secondly is the desalination of water. Thirdly is the purification of organic solvent. And lastly is the purification of drugs from chemical processes. Now I'd like to pass the presentation to Yap Jun Yong to continue on about the design aspects of the case study. Thank you.
Next, we will talk about the design consideration for our distillation columns. So there are four, which are the design pressure, temperature, material of construction, and also the vessel support. So first we'll talk about the design pressure and also design temperatures. So by using a general rules, the design pressure is about 1.254 bar and temperature is about 131 degrees Celsius. So for material construction, we choose a stainless steel because the methanol is a polar solvent and galvanic corrosion will occur. Next, for the vessel support, we will choose a skirt support because our orientation for our distillation column is mostly vertical. For the design procedure, there are four, which are the process design, physical column design, hydraulic design, and also mechanical designs. So I'll talk about the process designs. First step, we need to determine the flow rates. So we will use the overall mass balance, also a material mass balance. The second step, we need to determine the number of stage and also reflux. So by using this equation, we can draw a graph and we found that R minimum equal to 0.848 and also R from the equation given equal to 1.35 R minimums. Okay, so we can get this value. So for next step, we need to substitute equations inside these equations and number of theoretical stage equal to 10 including a reboiler. Next, we need to determine the liquid and vapor flow rates. Since all the feeds in saturated liquid, so all feed will join the shaping sections. So this is a summary for our process design. Next, we will talk on the physical column design. So actually, we need to find the flooding velocities. So to find a flooding velocity, we need to determine K1s. And K1 is related to liquid vapor flow factor by a graph. So by using this graph and assume flat spacings equal to 0.5 meters, the flooding velocity can be found. So since our design is 80% of flooding velocities, so the column diameter can be found also. To calculate the column height, the column efficiency given from question is 70%. So, and we can calculate the number of stage, and the height will be equal to the tray spacing times the number of stage. And addition of 4 meters is added on the top and also 10 feet at the bottom. So the summary for our physical column design is shown here, which include diameter, height, and also volume of distillation column. Next, I will talk on the plate hydraulic designs. So first step, we need to determine the liquid flow patterns. So liquid flow rate and also column diameter can be calculated from the previous sections, and from the figure here, you can find out that is a single pass plate. For the second step, we need to determine the downcomer area and also active areas. So downcomer area from the question is equal to 0.12 column areas, and the active areas is equal to column area minus 2 times of downcomer areas. So in this stage, we assume that wheel height equal to 50 millimeters, the diameter of hop equal to 5 millimeters, and also the thickness of plate equal to 3 millimeters since we use a stainless steel. Next, we need to check for wrapping. Okay, to calculate the wrapping velocity, we need to find a K2 values. So the K2 value is related to the height of liquid craze over wheels. So by using this equation and this figure, we can find that our wrapping velocity equal to 14.4 and our actual velocity equal to 16.36. Since it is well above the wrapping velocity, so our result is acceptable. Next, we need to measure the pressure drops. So the pressure drops is almost equal to 106 millimeter liquid after adding the pressure drop across the dry plate, residual head, and also the weld height, and also the height of the liquid crest over wheel. Next, we need to check the entrainments. The percentage of flooding velocity will be equal to the actual velocity over flooding velocities, which is almost equal to 56%. And then we use this graph to find our fractional entrainments, which is equal to 0.012, since it's below the upper limits, which is 1, and the effect of the efficiency is considerably small. And these are the summary for our flat hydraulic design. The last design is a mechanical design. First, we need to determine the trial layouts. So the unperforated strip round plate edge and also the wall coming zones are assumed to be 50 millimeters. And we use this figure, we can find that the delta C equal to 99 degrees. Next, we need to determine the crumbing area zone and also the perforated areas. And we can find out from the mean length for each zones. And we found out that the total area of perforation equal to 0.47 meters square. Next, we need to determine the hole pitch. The hole pitch can be calculated by using these equations, and we found out that LP over DH lies between the normal range of 2.5 to 4, and our hole pitch is equivalent to 30 mm. Next, we need to determine the number of holes. Diameter of one hole is assumed to be 5 mm. The number of holes will be equal to hole active area divided by the area of one hole, which is equal to 3157. And these are the summary for our mechanical design. I will pass the section to the next person. Thank you.
The demand of electricity depends on the energy or work needed for chemical processes. It can be purchased from a local supply company or generated on-site. To generate on-site, gas turbine cogeneration plant with a waste heat boiler is used. Cooling water is used to cool or condense hot stream. The range of cooling is between 120 to 40 degrees Celsius. Below 40, refrigeration or chill water will be used. If the ambient temperature and humidity are high, then a cooling water system will be less effective and air coolers or refrigeration will be used instead. Steam is used to heat a processed fluid stream. Steam can be classified into high pressure, medium pressure, and low pressure steam with different temperature and pressure. The advantages of using steam as heating utility are high heat of condensation, high heat transfer coefficient, easy control of temperature, and it is non-hazardous.
In design of distillation column, a few codes and standards are used. First, ASME boiler and pressure vessel code includes selection of the material of construction, maximum and minimum design temperature and pressure, as well as corrosion allowance. Second, ISO 2007 includes loadings such as wind, earthquake, transportation, handling and installation loads, and degradation mechanism. Besides, during the selection of material, the manufacturer should get the material identification and certifications. From safety aspect, methanol is flammable and poisonous. This may lead to deflagration type of explosion and fire, thus harms the safety of operators. Other than that, overpressuring of distillation column may lead to vessel rupture and explosion, leading to capital and production loss. To prevent this, safety relief devices such as safety relief valves are installed to reduce the pressure of the vessel.
Next, we will be discussing on the cost estimation for distillation column. Equation L4 will be used to calculate the bare module cost, and these are the parameters from design that will be needed to calculate the cost of the vessel. Firstly, we want to find the value of CP0. By using our volume, we get the purchase cost per unit volume from figure A7, and we calculate our CP0 as shown in the calculation here. To find B1 and B2, which depend on type of equipment, we use table A4. For material factor, the ideal number of process vessels made out of stainless steel is 20 from table A3, and thus from figure A18, Fm equal to 3.1. For pressure factor, the equation is given here in the slide. As our column thickness is smaller than the minimum allowable thickness and design pressure is bigger than negative 0.5 bar, Fp is equals to 1. By substituting all the value into equation A4 from before, we get our CPM 2001 for vessel as shown here in the slide. To get it in 2020, we use index, and our final CPM in 2020 is 544,803 ringgit.
Next, we will be calculating the cost of the tree. First step is to find the purchase cost. From the table given, we will get the value of K. We will use all of this data to get the value of purchase cost in 2001. Second step is to find the purchase cost in the current year, which is 2020. We will use the formula of index to get it. Third step is to find the bare module cost factor, which is 5 PM, with the help of table E6 and figure A90. For the first step, we will calculate the quality factor. For our case, it's 1.15. Put all the value from the step 1 until step 4 to get the bare module cost of the tree. Thus, our distillation column is about 562,000.